Let's get started for the day. Let's continue from where we left last time. We were looking at the property of linearity, and that in turn consisted of two sub properties, namely additivity and homogeneity. And if the system is both additive and homogeneous, it is linear. And these two properties can be combined like this, and this gives rise to the well known principle of superposition. And using mathematical induction, we can extend this principle of superposition as follows. Remember, superposition applies only to just two inputs. Using induction, this can be extended to n inputs. And this term k going from 1 to cap n ak times x k is called as a linear combination. Now let us try to extend this. Let us look at this first. So we know this is true. Additivity for two terms can be extended up to cap n terms. So the question is k going from ak. So this is the input. So this is passed through the system. The system output, of course, is ak times t operating on xk. The question that we want to ask is this true? Additivity, when it is extended using induction, is true for cap n terms. Is it true for infinite number of terms is the question. If it is true for cap n terms, is it true for infinite number of terms? Actually, you have assumed that it is indeed true for infinite number of terms in signals and systems. Okay, very good. Fourier series. So what happened in Fourier series? Yeah, so you had an input that was periodic that was expanded in Fourier series, and then, so where did you use this? Yeah, very good. So indeed, in applying periodic signals to an LTI system, you expanded the input in terms of its Fourier series components, and in general the Fourier series has infinite number of terms, and when it is applied to an LTI system, you indeed assumed that the output was of this form without even questioning whether finite additivity is true for infinite additivity. We will assume that infinite additivity is indeed true. All I want to point out to you is it does not automatically follow. This is a linear combination, and by linear combination we always mean finite linear combination. And if it is true for finite n, it does not automatically true, it holds for infinite number of terms. Additional conditions have to be met for superposition to hold as n tends to infinity. We will assume that these conditions are satisfied, and we will leave the worrying to the mathematicians. We will happily use this. Now let us try to clean one important consequence of homogeneity. So if x gives you y, c times x must give you c times y for all c. In particular, the above is true for c equals 0, and hence if the input is 0 times x, which is 0, the output also must be 0 times y, which is 0. So 0 input produces 0 output is what this is normally termed as. When we say the input is 0, we mean that the input is 0 for all time, right? And it's important that this should not be misunderstood to mean that whenever the input is 0, the output will become 0. That's not what is meant by this. So let us look at a system y of n equals 3 times x of n plus 2. So is this system linear? Y and x appear to be linearly related, but the system fails the linearity test because homogeneity does not hold. If the input is 0, the output must also be 0, whereas if x of n is 0, the output is y of n, which is non-zero. Therefore, the system is not linear, but it is also the case that the system is not non-linear. All right, this is what is called incrementally linear, which means that the difference between two outputs must obey linearity. So we will not get into incremental linearity beyond this point. We will just mention what this term means, and then we will leave it at that. And one of the consequences of this is, if you recall your RLC network with initial conditions, your capacitor had non-zero voltage or inductors had non-zero currents. Suppose the input is 0, the output will still be non-zero because of the transients caused by the decay of these initial conditions, capacitor voltages and inductor currents. So, from the strict definition, the system is not linear because 0 input must produce 0 output, and an RLC system not being linear seems counterintuitive. So, what is happening here is, if you treat the initial conditions also as an input, then the overall response is sum of the outputs due to the initial conditions and the output due to the input with the initial conditions zeroed out, right. So, when you want to compute the output due to conventional input, you will zero out the initial conditions. Okay. If you take that approach, then systems with initial conditions are indeed linear. Again, the reason I am mentioning this is, some books treat these two things differently. If you treat the system like a black box, then the initial conditions are not accessible, which means the system is incrementally linear. If the initial conditions are not accessible, then you cannot go in and zero them out if you want to find the output due to the conventional input. If the initial conditions also are viewed as inputs that can be zeroed out, then considering other sources, then the system is linear. So, when you are referring to textbooks, you have to be clear as to which approach you are taking. If I am not mistaken, I think Lati follows the first approach, in which he assumes the initial conditions are accessible, which means you can zero them out and then you can apply your conventional input. Therefore, as far as Lati is concerned, the system is linear. Oppenheim treats the input as a black box, which means, strictly speaking, you do not have access to the initial conditions, which means in those cases the system is incrementally linear. And this is, as far as RLC circuits are concerned, it is linear constant coefficient differential equations. The counterpart is, for discrete time systems, it is linear difference equations with non-zero initial conditions. And in the case of systems with initial conditions, you solve them using unilateral Laplace transform. I do not know whether this was part of your earlier course. You can use unilateral Laplace transform with initial conditions and then solve in a very simple manner the circuit. And the corresponding counterpart is linear constant coefficient difference equation, and you can solve them using unilateral Z transform. Whereas in this course, we will be considering only the bilateral Z transform, and then we will draw parallels to the bilateral Laplace. Now, let us move on to the next property, namely time invariance. Suppose the input x of n produces y of n. If x of n minus n naught produces y of n minus n naught, the system is time invariant. So, this is no different from what is happening in the continuous time case. And the intuition behind this principle is, if you delay the input by a certain amount, the output gets delayed by exactly the same amount. For example, if you apply x of n minus n naught, if the output is not y of n minus n naught, but it is y of n minus n1, then the system is not time invariant. The delay has to be identical. So, intuitively you expect the same output to appear when the input is applied at a later time. So, the only difference is a delay in the output, and the delay is identical to the delay suffered by the input. So, output delay must be identical to the input, and loosely speaking, if system parameters do not change with time, the system is time invariant. For example, if you had a system that had a time varying gain, then if you apply an input later, the gain of the system would have changed. So, you cannot expect the same output except for a delay. So, that is the intuition behind this time invariance property. And time invariance also is called shift invariance. And in terms of pictures, I have shown this in terms of continuous time plots. The same thing applies in terms of discrete time as well. So, here you have a certain input producing a certain output, and when you delay it by tau, you get exactly the same output except for this delay, and the output delay is identical to the input delay. And another way of looking at time invariance is in conjunction with the shift operator, which we call it as S. The system operator is called as T. So, if you had x of t applied, the shift operator will shift it by t naught in the continuous time case and n naught in the discrete time case. So, these are the corresponding shifts that this system produces when an input is applied, and you can use the suffix tau if you want to explicitly mention the delay. And the shift operator is also called as the delay operator, and if the delay is negative, it advances the output signal. So, for time invariance, again this parallels exactly what you have learned for continuous time. You apply the input to the system, you get an output, and you shift, you get n minus n naught. So, this is one part for the test. The other part for the test is you take the input, first shift it, you get the delayed input, then apply it to the system, then you examine the output. If W of n, which is in the second case, same as the output that you got in the first case, then the system is time invariant. Again, this is no different from the CT system test. Take the input, apply it to the system, delay the output, that is one part. Take the input, delay it, and then apply it to the system, check the output. If these two are equal, the system is time invariant. So, these are the two branches. First you operate on the system and then shift, whereas in the second case you shift and then operate on the system. And system is time invariant if these two operators commute. If S t equals Ts, the system is time invariant. Again, continuous time example is easy to see, you might have seen this already. If you take the output, the system is y of t equals x of 2t, you shift the output, replace t by t minus t naught, and if wherever t is there, if you replace t by t minus t naught, you get this. So, the output is 2 times t minus 2 times t naught. On the other hand, if you shift the input and then apply it to the system, all the system is going to do is wherever t is there, it is going to replace t by 2t. So, clearly these two are not the same, and hence the system is time variant. Okay. The intuition behind this is if you take the output and then shift, in the first case you have a certain shift, whereas when you take the input, shift it and then apply it to the system, because the system replaces t by 2t, the shift reduces by factor of 2. That is why the shifts are not equal. And you can easily verify the same is true for the discrete time counterpart, y of n equals x of cap n times n. So, check for linearity and time invariance, and here is what is called as a modulator. So, x of t multiplied by cos omega naught t is this. So, is the system linear, the system time invariant? Based on what I had already mentioned, if the system has a time varying gain, you can expect that the system to be time variant, and here cos omega naught t can be thought of as a time varying gain, and hence if you check for time invariance, you will find that this will fail the time invariance test, and this is indeed time variant. And linearity and time invariance are independent. System can be linear and not time invariant and so on. So, y of n equals x of n squared. So, this is clearly time invariant, because if you shift the output, that is one part. The other check is you shift the input and then apply it to the system and then compare the outputs. Clearly these are the same. So, clearly the system is time invariant, and very easy to see that this is non-linear. Therefore, these are independent properties. System can be linear but time variant, can be non-linear but time invariant, and so on. So, 4 combinations are possible. So, later we will focus on systems that are both linear as well as time invariant. The next property as far as systems go is systems with and without memory. So, if y of n naught depends only on x of n naught, then the system is memoryless. The other name of course is static. So, the current output depends only on the current input, or the present output depends only on the present input. Otherwise, the system is said to be having memory. It is non-memoryless or dynamic. So, y of n equals x square of n is clearly a memoryless system. On the other hand, y of t, which is the running integral from minus infinity to t of the input, is a CT system that has memory. And here is another simple example. Y of n equals x of n plus 1 is a DT system that has memory. And the reason why this example is mentioned is usually when we talk about memory in ordinary language, we are used to always memory of the past, because in ordinary circumstances memory of the future does not make any sense. Whereas in this context, y of n equals x of n plus 1 is indeed a system that has memory. The next property is causality. So, if y of n depends only on the present and past inputs and past outputs, the system is causal. In other words, y of n naught depends only on inputs for n less than or equal to n naught and outputs for n strictly less than n naught. As far as causal systems are concerned, the current output can depend on current input and all past inputs and past output. If this is not satisfied, the system is non-causal. So, y of n equals x of n minus 1. So, this is a very simple system that is causal. Y of n equals x of n plus 1 is non-causal because, for example, y of 0 depends on x of 1, so called future input, and y of n equals x of n times cos of n plus 1. This is still causal because as far as causality is concerned, it is the input that we are concerned with. You should not be fooled into thinking you see an n plus 1 term here, therefore this might be non-causal. It is not, right. So, causality applies only to the input part. So, you are talking about the case where you are applying two inputs, all right. So, in general, when you talk about an input, you assume an x of n to be a generic function, right. You do not talk about x of n taking specific forms. When you talk about input output relationship, some arbitrary input is there and then you find out what the output is. So, it is in that context we are talking about causality here. So, this is general, right. Expected input is some arbitrary input, it is not tied to any specific signal. So, okay, right. So, now what is z of n plus 1? Okay. So, now remember we are now talking about single input single output systems. So, what you are raising is something that is related to MIMO, multiple input multiple output. Okay. So, that theory surely that can be addressed in that context, but as far as this is concerned, you are only worried about single input single output, right. So, does that answer that question? Okay. So, system can be causal or non-causal based on these definitions. And again, if y of n equals x of minus n as an example, so if you look for test for causality, superficially it appears to be causal because y of 0 is x of 0, y of 1 is x of minus 1 and so on. But remember, causality must be true for all n, y of minus n is x of 1 and the causality test fails. So, these simple things might trap you into giving the wrong conclusion. So, make sure you test these things completely. So, as an exercise, very easy to do, y of n equals x of m times n, is this causal, y of t x of 2t is this causal. Again, this is no different from what was happening earlier. You would be given an input output relationship and then you have to test for various system properties. So, in this case we will focus on discrete time systems and you should be able to see the parallels to continuous time systems. Maybe you may have done some of these for discrete time systems as well. So, that is fine. So, this is just a recall, some overlap is fine so that it strengthens your understanding. The next property we will look at is whether or not the system is stable. Whether the system is stable or not depends upon the stability criterion. There is no one universal stability criterion, and the most common stability criterion is bounded input bounded output. That is, if you give a input that is bounded, then for stable system you expect the output also to be bounded. If for a bounded input you get an unbounded output, then the system is not stable. Of course, if you give an unbounded input, then all bets are off. So, the input is bounded by Bx, then if the output also is bounded, say By, then the system is bibostable. So, y of n equals x square of n is clearly a stable system because if the input is bounded, output also is bounded because all you are doing is you are merely squaring the input. On the other hand, if you have y of n equals the running sum of the input from 0 to little n, then if you give this system the unit step as the input, the output is n plus 1 times u of n. Clearly u of n is a bounded input, whereas n plus 1 times u of n is not. So here if the input output relationship is this, then this system is not bimostable, because here is a simple example that blows up when you give it to this system. And the corresponding counterpart for the continuous time system is the running integral. Here is the running sum, CT counterpart is the running integral. Here if you give again x of t to be u of t, the running integral is a ramp which is not bounded. And generally system properties are independent. We saw already linearity and time invariance are in general independent. So you can have any combination of these properties. However, if the system is memoryless, then it is necessarily causal, right? So if the system is memoryless, it cannot be non-causal. So some properties have dependence. So again, this is something I want you to think about. What about stability of a memoryless system? What about time invariance of a memoryless system? Okay. So now let us take one concrete example and then check for all these properties. So we want to check whether the system is linear, time invariant, memoryless, causal and stable. Again, as I had mentioned earlier, if a property holds, you have to give the general proof. To show that it does not hold, a single counterexample is enough. So now let us look at this particular example. So clearly y of n equals x of 1, y of 2 is x of 2 and so on. So y of n equals x of n for n greater than or equal to 1. Y of 0 is 0 always, that is how this input output relationship is, and y of minus 1 is x of 0, y of minus 2 is x of minus 1 and so on. So it is x of n shifted by one sample to the left. So this is what you get as the output as far as this system is concerned. So for linearity, if x1 gives you y1, x2 gives you y2, then a1 x1 plus a2 x2 should give you a1 y1 plus a2 y2. So that's the check you need to make. So let us assume the input is x3. So x3 gives me y3. x3 in turn is a1 x1 plus a2 x2. So since x3 is the input, this is exactly the input output relationship. All I have done is I have replaced y by y3 and x by x3, otherwise everything is the same. But now we know what x3 is. x3 is nothing but a1 x1 plus a2 x2. So for various indices, I have replaced x3 by the corresponding definition. Therefore, it's easy to see that y3 is indeed a1 y1 plus a2 y2 for all n. Therefore, the system is indeed linear. The next check is for time invariance. One intuition you can have is, remember, y of 0 is always 0 for this particular example, the way it is been defined. So we want to check whether x of n minus n naught produces y of n minus n naught. In particular, does x of n minus 1 produce y of n minus 1? So here is one input I have taken, and remember, y of 0 is always 0, and for all positive indices, the output is the same as the input. For negative indices, all you need to do is shift the input by one sample to the left. So that is exactly what is happening here, because y of minus 1 is x of 0 and so on. Alright. So this is indeed the output for this given example. Now the first step is to shift this by one sample to the right. If I shift this, the entire curve shifts by one sample to the right. In particular, y of 0 after the shift by one sample will no longer be 0. I have not shown the shifted curve here, but easy to see that you can shift this by one sample to the right. So this 0 will come here. Now let me shift the input by one sample to the right and then check the output. So this is the shifted input. by one sample to the right, and here I get the output, and notice that the output at y equal to 0 will always be 0. So, this is shift by one sample to the right, by definition I will get 0 here. So, this and this shifted by one sample to the right are not the same, therefore, this system is time variant, that is all. So, shifted input does not produce shifted output, therefore, the system is time variant. Since y of minus 1 is x of 0, the system is non-causal, and for exactly the same reason the system has memory. And if the input is bounded, remember for n greater than or equal to 1, the output is the same as the input. At n equal to 0, the output is always 0. For n less than or equal to minus 1, you shift by one sample to the left. So, if the input is bounded, the output always will be bounded. Therefore, the system is bibostable. So, system is linear, time invariant, non-memoryless, non-causal and stable. So, this is the typical kind of exercise that you should be familiar with in terms of a question in the quiz or the exam. Given a certain input-output relationship, are you able to test for each of these properties clearly without any confusion, right? There should be clarity in your steps, that is all.